So the last part of chapter 17 is about moving reference frame, and the idea is basically exactly the same as the sliding contacts, the derivation, everything. So you have a point of interest A, which is being observed from a primary reference frame, which is fixed and inertial, and then it's also observed from a secondary reference frame, which is moving. It can translate and it can rotate at the same time. And you want to relate the velocity of A as seen from the moving frame to the velocity of A as seen from the fixed frame. You want to relate them to each other. The derivation is exactly like the previous case, no difference. You can show that V of A in the inertial is equal to V of the moving frame origin itself in the inertial plus V of A relative to the moving frame and the effect of rotation of the moving reference frame that creates this extra velocity term. And similarly, acceleration of A relative to the secondary or moving frame, A relative, can be related to acceleration of A in the primary reference frame when we add 4 extra terms. The acceleration of the origin of moving with respect to the fixed, plus the Coriolis effect, plus the tangential acceleration, plus the normal acceleration. And all of these 3 terms come into existence because of rotation of the moving frame with respect to the fixed frame. So we have seen these formulas in section 17.6 and how they are derived, so nothing new. It's just the application that I want to emphasize. So here we're going to look at example 17.11, the one that I mentioned in the previous lecture also, that you have a ship, and this warship is moving north at a constant speed of 15 meters per second. And it's also turning toward west at a constant rate of 5 degrees per second. Okay? So we know in which direction it is moving and how it is turning with respect to the fixed reference frame on the Earth. And then the radar of this ship is catching up the relative position, the relative velocity, and the relative acceleration of the helicopter with respect to itself to be these 3 vectors. We want to know what is the velocity and what is the acceleration of the helicopter measured with respect to the fixed reference frame on the Earth. Okay? So, and by the way, we have to use the coordinate system shown here. So the ship is moving along X direction and it says it is moving to north. So north for us is going to be X-axis. Y is going to be upward, and therefore you're going to see that Z-axis is pointing toward east. So if I look at this ship from the top, basically, I would see the ship. Oh, something like this. Now take it from me, assume that it's the ship. And the coordinate system are, this is X, which is toward north. This is Y, which is out of the plane toward U. And then Z is toward east. And this is the velocity that this guy is going right now. It is 15 meters per second, right? And then this guy is also turning. So it is also turning. So it is turning toward west, as it says. So it is turning this way also at the same time with some constant omega of 5 degrees per second. So this is constant, and this v is also constant. What we need to do, first of all, here we call B to be the ship. So here A for us, A, the object of interest, is the helicopter, and B, the moving frame which is measuring the helicopter, is the ship with its radar. Okay, and of course we have a frame attached to the Earth. So what I would like to do is I use cap XYZ here. So this is cap X, this is cap Y, and this is cap Z. And then we also have a frame attached to the ship, which is small x, small z, and small y. So what we need to find is the velocity of the helicopter with respect to the ground frame, and also acceleration of the helicopter with respect to the fixed frame. And we know that r of a with respect to b is given, v a relative to b, of course, is given, and a of the helicopter relative to the ship is also given. So then it shouldn't be such a huge deal. All we need to apply is the formulas that we know. So we say v of a relative to the fixed frame is equal to v of the ship with respect to the fixed frame plus omega of the ship cross r of the helicopter with respect to the ship plus v of the helicopter relative to the ship. Okay, so that's all we need to do. And clearly you see that v of the ship is 15 units in the x direction, so it is going to be 15I. Then we have to convert omega into standard units. And then if you look here, it's 5 degrees per second, but the standard unit we have is radians. So we need to make sure that omega here is converted into standard units. So this is also equal to 5 over what? 5 times pi divided by 180, right? That's how you go from degrees to radians. So 5 divided by 180 is 1 over 36, so it is going to be pi over 36 radians per second. And since this omega is clearly about the y-axis, and it's positive y-axis, so it is going to be positive j, so this is going to be pi over 36j, that is your omega, cross r of a with respect to b, which is given to you directly. It is 420I plus 236.2 j, and then plus 212k, and then plus VA relative, which again is given to you by the radar, negative 53.5I, then plus 2j plus 6.6k. And all you need is to carry out the cross product and simplify, and if you do, you are going to get negative 20I plus 2j and then minus 30.1 K unit meters per second. So clearly you see that this vector, which is what the radar measures on the ship, is different from what you should report to the headquarters. Clearly, right? They are different because of the effect of the motion of the ship and rotation of the ship. And then similarly, you say acceleration of the helicopter relative to the Earth is acceleration of the ship relative to Earth plus acceleration of the helicopter relative to the ship plus the Coriolis effect to omega cross VA relative, and then plus the tangential acceleration, and then plus the centripetal or normal acceleration. Okay, so you have to calculate all terms. And now AA relative is directly given to you, no big deal. Point for I minus point to J minus 13K. Then omega is found. We found that omega is pi over 36J. VA relative, we have it. It's this guy here. Alpha is what? Since omega is constant, alpha is going to be what? 0, right? Because omega is constant. So this term is 0, so life is good. Omega we have, both of these guys are pi over 36J, and then R of A with respect to B is also given. Okay, that was this vector here. So we have everything here except for this A of B. And some of my students in the past, I remember when I asked them what is A of B, which is the acceleration of the ship with respect to the Earth, they directly say 0. Why? Because it is moving with a velocity of 15, which is constant. And initially it might be tempting to say so, but the problem is this guy is not going on a straight line. It is what? At the moment turning. It is turning. It has omega. It is turning. It is going on a circle. And we know when you go on a circle with the constant v, what term do you have? You are right. The term that you have is called centripetal acceleration, right? So you do have a centripetal acceleration because this guy is going over a circle. And so it does have an acceleration component toward the center, some AN. So clearly, if you look at AN, it is toward west. So it is going to be opposite of the z-axis. So it's negative k. And what is the magnitude of normal acceleration? If you remember, normal acceleration magnitude when you're going with a constant velocity around the circle with radius r and with omega, it was r omega squared, or it was v squared over r, right? Where r is the radius of the circle. But what about this case? Nowhere in the problem it says how big is the radius about which the ship is turning toward west. Never says that. We don't have that information, so r is not given. But if you want, what you can do is, there is a third formula. Actually, let me keep this. there is a third formula which is equivalent to these two. So what I do, I write this as R omega times omega, right? And what is R omega? That's V, correct? So I can also write it as V times omega. So that is the third formula, equivalent to the other two. I can use this one. This one, the good thing about it is it doesn't need R. It just needs V and omega. And guess what? We have both of them. We have V and we have omega. And then again, we know it's negative Z direction. So this guy, the magnitude of it is going to be negative V times omega in the K direction. And now we can simplify everything. So now, if we just carry out the cross product, then we are going to get negative 1.65 I, then minus 0.2 J, and then minus 6.59 K meters per second squared. And clearly, again, you see this number, the acceleration of helicopter with respect to the ground, is different from what? What the radar measures, which is this number. You see, they are quite different except for the J components. And why is J component not touched? Because the rotation of this ship is happening about J component, so that component is not touched when you carry out the cross products. But everything else will be touched. Okay, so now, just as a final thing, just want to remind you one more time, if now you have the picture of the helicopter, and somebody says, okay, could you draw the free body diagram of this helicopter, and then study the forces acting on it, pixelated helicopter, right, which is like gravity, and then if it is moving in this direction, then you have the drag force, and then you have the lift force, right? And then you have a thrust, correct? So when you say sum of the forces on this helicopter is equal to mass of the helicopter times acceleration of the helicopter, which acceleration goes here out of these two? Yes, you are right. This one, that is with respect to the inertial. This one should go over there for kinetics analysis, not the one that radar does measure, okay? So just keep that in mind.